And if so, please be aware of that. So I would also ask not to take any photographs of slides or anything, and then we will make sure that the information that is freely available becomes available. Thank you very much, Irene. Without any further ado, you can introduce us to this very important subject. Thank you.
Okay. There we go. There we have my first slide. Yes, thank you so much. Sorry about that. This is all, you know, you think we'd never done a Zoom presentation before. This is not the presentation I'm looking at. I'm looking at this presentation. Yes. So as Patty already said, this is part of a bigger project we are doing on this thing called the landing obligation. And because we have quite a few people coming in from outside of Northern Europe, which is great, I thought I'd give a brief introduction in what we've been doing and where this whole webinar fits into what's going on in the policy land in Europe right now. So the landing obligation, which was introduced as part of the CFP reform in Common Fisheries reform in Common Fisheries Policy reform. So that's the overarching policy framework for fisheries in Europe, the reform in 2013. And part of that was a discard ban, or as it was named, the landing obligation, which says that as of 2019, all catches of managed species will have to be landed. So it means that everything you catch, if it's a managed species, if there's a quota attached or something, you will have to land it. There were already in the regulation some exemptions foreseen. One that was for proven high survival, one for species that were prohibited because they were endangered or something. And there is a de minimis, I won't go into that, but that's sort of a percentage of catch that you can sort of still discard to handle an overshoot of quota. So this was a problematic immediately we could see for skates and rays because the way they are managed in the EU. So skates and ray in the North Sea and Northwestern waters, that's where we focus. There are three different ways they are managed. One of them is through a group TAC. This is all the species are that are basically have a commercial value are taken together as a group. So it's one TAC that's divided up between countries. For the North Sea, at least at 6 species. Then there are prohibited species. Those are species that are very rare. You don't want them to be caught. These are all species that used to be commercial species in the past, but no, not anymore. And we also have species that have absolutely no management, something else we should be focusing on a bit more maybe, but is another project for us. So this is where we were. And the problem, of course, we see when you manage things like a group, it gets very hard to divvy up the number of fish that you can actually land individually because it's a group. And then also because in our fisheries, because in our trawl fisheries, skates and rays tend to be bycatch. There's very limited. There's only limited targeted catching of these animals. They're all bycatch in other species. You immediately see that when you're sort of going for something else that's more abundant than the skates and rays, and you have to land all your bycatch in a restrictive TAC, you might have to show what we call the choking of another fishery. So this is why we're looking for a solution back then. Both NGOs who thought maybe we don't want to land all of them, and the fishers who said, okay, we don't want to close our fishery because of we have too much skate bycatch. So we started looking together for how to fix this, and that's how we came up with the rationale for the exemption. It's from 2018. So because by 2019 they had to be landed. So there wasn't really an option back then to divvy up the group TAC with individual TACs because there was just no data available on how to do that. Selectivity the best thing, of course, is not to catch them in the first place. So more selectivity could be an option, but that needed further study. And we knew they had a pretty high survival. It just wasn't really proven for every species in every year. So that's why they said, you know, it is a high survival exemption with caveats attached. And because, you know, if it's correctly used, it can actually lead to filling some of the data gaps we have on the survival, on the catches, on the discard, and to have a sustainable long-term management solution. So what happened then, how the system works, you have something called the Scheveningen group. Yes, I won't ask anybody who's not Dutch to repeat that. But that's the group of North Sea member states working together, and they come up with something that was called a joint recommendation for an exemption. for the skates and rays for the landing obligation. And it was to have best practice guidelines on appropriate avoidance and selectivity measures and fill the data gaps on survival. And also, make sure all fish that come on board are discarded promptly. But you should also have part of it should be best practices on avoiding bycatch. And this was supposed to be part of the 3-stage rocket. This actually made it, I'm so proud of this, into the official policy document, this lovely rocket. So the first stage of trying to avoid bycatch is avoidance. So things like avoiding spawning areas, real-time closure, real-time communication, closures, move-on rules when there's high abundance, aggregations, that sort of things. Second stage is selectivity, so things like deterrence that we're talking about today, really cool. Gear adaptations, escape panels, grids, that sort of thing. And the last stage is, of course, the handling. So once you have them, if you haven't been able to be selective, then get rid of them as quickly as possible. Handle them quickly, keep them wet, that sort of thing. So those were supposed to be the elements of that those best practices. And then the idea was that sort of we have some ideas about gear impact and potential for survival, and that overall you actually have the survival going up and the gear impacts going down. So over time, that was the idea behind it. So for these best practices, there was a roadmap, and the project that we are doing right now is evaluating the uptake of that roadmap. And there should be a program of measures which should include mandatory best practices for spatial temporal avoidance measures and gear selectivity enhancement. Mandatory is between brackets, and so it means you don't have to be mandatory, and nobody was. So there is only a limited number of mandatory actions, as we have. So this is our conclusions, is that we only have a limited number of mandatory actions, and actually most of those predate the landing obligation coming in, because the quota for skates and rays was always quite limited, reductive. There were all kinds of measures that you could only land, for example, for the Dutch vessels, they can land, I think, maximum 50 kilos per trip. So there is already a mandatory action there, but that's a PO, a producer organization measure. There are some voluntary measures, but we have no data on uptake. They're mainly focused on handling on board, so only the last stage of the rocket. But there is promising research and some gears that can already prove that deserve further scrutiny. So the next phase is actually what we're doing today, looking at those new technologies. Then this year, there's a reason why we're doing this year, because this summer there's on this end of the year there's a revision of the exemption for skates and rays coming in this year, and member states have to come up with a justification why they still need it. There's still good reason to have it, because there is evidence for high survival for quite a few species by now. But it also should have some warm of what did we do with this selectivity thing. And there's also a new plan from the European Commission on an action plan to conserve fisheries resources and protect the marine ecosystem, which also has quite a bit on bycatch in there. So there is. This is all part. This webinar sits perfectly with where we are in the policy land. That's what I wanted to introduce. And from that onward, I'm gonna stop sharing, and that's what I do here, and hand over to our first speaker. And this is the reason why I still hope we still will have Twitter for time to come, because the reason we have this speaker is that he posted his paper on Twitter. I saw it and immediately wrote to him saying, "Hey, do you want to be in my webinar?" And he said yes. So, let's hope Elon Musk doesn't screw that up for us. Vincent Roelt, he is from Australia. So for him, it's really late. And he works at the Center for Integrative Ecology, the Center for Integrative Ecology in the School of Life and Environmental Sciences, Deakin University in Australia. And he did some research on bycatch of skates, avoiding skates eating his oysters in an oyster farm, right? So your co-host, so you should be able to share your screen without me giving you permission.
Yeah, should work.
Great, thank you.
Kind of okay, cool. Okay, so thanks for having me, Irina. It's great to come over from sunny Australia, even though it's 9 o'clock right now. I'm going to talk about some work. I'm also touching up on magnets for some previous work that we did in this kind of stuff. And this was across a few different institutions in Australia. So Macquarie Uni and Uni Newcastle, Deakin Uni, and also Graham Barclay oysters. And so hopefully, because this is a little bit out there, hopefully it might stir some new ideas. So where I first started working in this area was in a local fishery down here on the Central Coast near Sydney. It's a trap fishery, ocean trap fishery. So their aim is to catch a whole bunch of different fish species, and they set out these traps. And they had this issue with these cute little blind sharks getting into the traps and causing havoc. And the fishers themselves had a pretty good idea that when they caught these sharks in their traps, they had this side effect of catching fewer fish. So there was an actual financial cost to them. And these sharks were also very high post-catch survival, but they were also a pain to get out of their traps. And so they kind of enlisted us to try and come up with a solution. At the time, magnets were all the rage. And so because these traps have 4 small entrances, you can see 3 of them in this video, we thought we could put magnets on the entranceways to these traps and hopefully reduce bycatch of these elasmobranchs. And the first thing that came up with this research in this fairly wide trial, I think we hit something like 900 deployments of these traps with controls and procedural controls as well as magnets. And they definitely did have an effect of catching these sharks on the actual fishes themselves. So there was definitely an impact, a negative impact on the fishery by these sharks, even though there's no effect on the shark populations themselves. They're least concerned. There's very little impact of the fishery on the species, but definitely catching fewer sharks. But what was quite interesting is that magnets, incorporating magnets into these traps resulted in about 30% reduction in bycatch from these sharks. And because of the effect of reducing shark numbers in the traps, the fishers themselves ended up with more targeted species in their catch. So it was kind of a case of win-win for this sort of fishery. But since then, sort of magnets have kind of lost their luster for a lot of these approaches. And I'm sure most of you know by now, magnets have some just physical limitations to them. The first of which is the inverse square law, where they lose a lot of their effectiveness just a few centimeters away. And you can have a magnet that can hold 20 kilos, be a neodymium, and be pretty much non-effective past a few centimeters. So they got that really low effect distance, which kind of limits where you can put them, which is why sort of these traps were kind of an exception, because you could force the sharks to go through very narrow funnels where they'd be really closely exposed to these magnets and they could act as deterrents. The other thing is magnets sound cheap, but at them across an area that would actually act as a deterrent, you end up with hundreds of these magnets, and that ends up being quite expensive on the long run. Magnets, of course, interfere with equipment. If you've got 1,000 hooks and magnets on each of those hooks, you can imagine the horrible tangle that you would end up with at the end of a run. And also there's evidence that they're highly species specific in terms of their impacts. And there's also some broader research that shows that they're not really an effective deterrence in cases where you might have social interactions between sharks and basically they goad each other into going for the food types. And so we kind of put magnets by the wayside shortly after this study in terms of research avenues. Now, this is where the oysters come in. We've been doing a lot of work in Wallace Lake, which is a lake nearby where the Uni Newcastle is placed. And it's notable that it's got the highest coverage of seagrasses across the east coast of New South Wales. So it's an absolutely massive estuary. And it also represents about half of the production of oysters on the east coast of Australia. So very large oyster production. And the way this aquaculture generally works in many cases, from the image of the right, you can see they put these oysters on trays. Usually they have to dry them and expose them for a certain amount of time to reduce growth on the oysters. And this basically looks like a giant dinner plate to a whole bunch of different ray species. And the growers have had historically a lot of issues with these rays coming in and basically targeting the healthiest crops. So they actually, according to the growers, target the oysters that are almost near sale size and can destroy a few $1,000s worth of oysters overnight. And so they've built these huge enclosures around these oyster paddocks to exclude rays, and historically they would just kill any ray that got close. So obviously there was a negative impact there. The growers themselves are interested in trying to reduce costs and increase environmental friendliness, and so they wanted us to come up with a solution. They were really still interested in magnets, so we still approached that, but we were interested in testing electric deterrents, specifically those that were used to try and deter shark species. And so we ran a preliminary experiment using the BRUV systems on the right. So it's really simple. It's just a pole that holds a bait tube. It's got a camera and weighted and a float. And we had 4 different treatments. We had a control with nothing. We had a ferrite magnet. We had a neodymium magnet. And the last one we have is the one on the bottom here on the right with a shark shield, so an electric deterrent on them. We deployed them initially in Jervis Bay, which is another estuary, but the reason we did that is, first of all, they host a lot of these smooth stingrays, which are one of the largest stingray species in the southern hemisphere, and there's heaps of them, so we knew that we'd get a lot of interactions. There's other species present, but the point is we'd be able to test out pretty quickly and determine which of these 3 different treatments were actually going to have some potential for the purpose of reducing oyster predation in the long run. This first one is a neodymium magnet, and a very powerful one. And you can see, hopefully, that this smooth stingray does not give a crap about the fact that it's interacting with these really strong magnets. And this was a pretty common thing throughout the whole experiment. The rays just had almost 0 reaction to these magnets. And these are 20 kilo pull force neodymium magnets. They're not, they're the ones that crush your fingers. So you can imagine they're really strong. You're not really going to get very much more powerful, and the rays just didn't bother whatsoever. If you compare this, though, to the shark shield, to the electric deterrent, you can see these rays don't really like it. And in fact, we had a very high number of interactions with the shark shield, and 0 times did the electric deterrent not work. And these are not small rays. These are rays that are over 100 kilos in weight. They're nearly 2 meters in width, in disc width. And so this for us seemed extremely promising. And across all these preliminary experiments, basically the magnets had 0 impact on the ray's behavior and their ability to actually get to the bait, whereas the electric deterrent was 100% effective across all the times that it interacted with the rays. So for us, that really threw us down the direction of, well, if we want to deter rays from oyster paddocks, then we're going to use electric deterrents. And so we rolled out this much broader experiment in Wallace Lake, right near to where these oyster growers operate. We ran into 5 different species of elasmobranch. They were all sort of flat sharks type species. 172 interactions in total with the control or the treatment. And the electric deterrent here was 85% effective. As you can see, this fiddler ray really did not enjoy interacting with the gear. And this is pretty typical of all the times you find these animals interact with these electro deterrents. You have a really sudden, immediate response when the animal actually interacts with that electric field, and it's pretty much always going to be a strong deterrent result. Now, I'd say the effectiveness in good conditions is probably closer to 100%, because what happens with Wallace Lake, there's a lot of current with the tides, and sometimes that anode would come back and curl around and basically reduce the area of effect to the point where it's no longer close to the bait tube, or it would even get smothered. And so we came out of this going, well, you know, these electric deterrents have a lot of potential, and that's kind of where we should be going to deter animals from these sorts of things. So bringing it back to the subject of this session, which is really about reducing catch in trawl fisheries, really, is how do we change this so that it's effective for trawls? So while the area of effect is much greater than magnets, it's still quite short in terms of distance. So you're talking 1 meter, maybe 2 meters at most. So if you think that you've got a trawl net coming in at about 3 knots, that's still not a lot of time to produce a deterrent effect that's actually going to cause the animal to go away from the trawl. And also the reaction of the animal needs to be in the correct direction. It needs to be the correct angle. So that's a lot of stuff to consider to try and develop something in this regard. This is why these sorts of electrodeterrents were more or less discounted for reducing bycatch of sawfishes in Queensland, in Australia, in our gillnet, in our prawn fisheries, because they didn't think the animal would have enough time to get out of the way, basically, from the trawl net. So where I think it might be a bit more effective is if you design something that's kind of like a turtle exclusion device that's designed to scare the shark into a direction where it ends up with a pathway outside the net. And obviously that requires a lot of development. The other thing to bear in mind is the voltage and the frequency of those electrodeterrents has a really big impact on its species-specific effectiveness. So bull sharks, for example, they're exposed to the same deterrent, which is very effective in white sharks, and the bull sharks just basically don't care. So you have to bear those things in mind. Scale can be problematic. Okay, so you can't just really make a really big array in this regard. They've tried to do this for recreational fisheries, basically these big buoys that you can just put in the water that have a really long cathode and anode to produce a really big area of effect, and they found that it's actually much less effective in that regard. What that reason might be is up for debate, but you can't just put a really big one and then just scare everything away. That it's not really that simple. And also, what are the effects on the target species for the fishery? So you might go, okay, well, fishes don't really have the sensory systems and capabilities that elasmobranchs, that makes elasmobranchs so sensitive to these things, but it's still 100 to 200 volts shocking you. And having been shocked repeatedly by these shark shields when I was working with them or working with these things, I can tell you it's painful and you react to it. And so obviously any fishery that's going to use this on a large scale is going to have some confidence that it's not going to impact their bottom line a whole lot. And if you want to read about this particular study, it's published in Regional Studies in Marine Science. That's all I have to say for today. If anyone has any questions, I'm happy to answer them.
If there are any questions, because I would take them now, because Vincent is 10 hours ahead of us, so he is in the middle of, it's almost bedtime for him. So if anybody would put something in the chat, otherwise we're going on to the next speaker, which is Allard. And for Allard, I need to pause the recording, and I'm going to resume. Okay, then if you can start sharing your screen and go on, and I can introduce you. So Matthew works at the Dutch Elasmobranch. You'll probably see it better himself, in Ireland, and they have been already been involved for a long time in gear adaptations for selectivity, also as part of this whole landing obligation that I introduced earlier. And he has actually some very nice results that he's been sharing us before, and I'm very happy that he can share them today as well. Thank you. Go, Matthew.
Okay, thanks, Irena. Yeah, this is, as Irena said, just which screen can you see?
I'm seeing your note screen, basically.
Yeah.
It's fine.
Yeah, I don't know why.
I sometimes end up like that too, and I'm perfectly fine looking at that. We can see what's coming.
It's just not big enough, is it? Sorry. I don't know. Whatever. If everybody's happy, I don't know why. Can I stop share and just see if I can share the other screen just for? I'll go through it quickly anyways. So, okay, share that. Can you see it now? Yeah, better. Okay, yeah, as Ryan said, yeah, work in Ireland. We've been doing some work, and it's oh, it won't move. Yeah. Okay, yeah, and just a little background, as Raina mentioned earlier, most of our work had been on the landing obligation, as Raina was talking about, but you know, in future we're going to be working, and currently actually the landing obligation is over according to everyone anyways, you know, we've moved on. But the current future, it's kind of technical conservation measures, climate change, seabed impacts, and sustainability. Obviously that's where we're going. So everything will follow on from there. But the two bits of work that I'm going to talk about were kind of under the land obligation, and they were in two of our sort of bigger fisheries, the whitefish and which is mostly haddock and whiting, and then it's the Irish prawn or nephrops fishery as it is, which is the Dublin Bay prawn, nephrops norvegicus as it is. So the two very distinct fisheries kind of work about maybe 60–70% of the Irish fleet. Within the whitefish fishery, this was again under the land obligation, as I said, and it was a kind of a measure that was developed to originally reduce sort of cod in the Celtic Sea, which is to the south of Ireland. And we just called it the raised fishing line, which was essentially a 1 meter gap between the ground gear and the fishing line, just below the net apart. The nets typically had about 30 odd droppers that were about a meter apart, each net being about sort of 30 odd meters of fishing line or ground rope. We did this twice, and the reason I'm saying that, it'll hopefully become apparent later. We did it on a twin rig initially, and then a single rig, sort of trial 1, trial 2. So it has had sort of a good assessment. We've been continuing on with this as well over the years. So as I said, race fishing line, very simply just remove the ground gear, put 1 meter of chain or rope droppers. Initially we put rope just because it was easy, some chain. We also sort of played around with different rigging configurations. You can see there sort of A or B and C. Sort of B was kind of the initial one. It was very simple. The C then was a bit more modified to hopefully kind of keep the fishing line up. So we had an extra third bridle to hold it apart. Then what we did in the prawn trawl, and we also, like this, it was to not sort of focused on ray, more on small whiting, and this was to the east of Ireland, between Ireland and the UK and the Irish Sea. Again, we like gaps, so we went and said we'd put it was a 2 fathom, but I've just for European friends, I put it as 3.6 meters, because even though we are a metric country, we still work in fathoms when it comes to lengths, it seems, with fishing especially. And again, with this, it's just 2 lengths of combination wire rope that were made up with 2 loops on each end, and you can see there what it did. Again, it just separated the trawls, it was like Alad was talking about in the quad rigs, or in this case, a half quad, which is just a half of the quad rig for prawns, and it just separated the two nets in that configuration. So one of the interesting things, what we started to do with this when we were working with it was, sorry, just somebody came in. What we did with this was we got side scan sonar, and this is an actual image of the net on the bottom of the ocean when we were testing it. So we could assess it before we tried it. So we knew, you can very clearly see these are 2 full-scale nets, 40 meter headlines, sort of the sort of quaternary sort of loops there, and the doors at about be sort of 60 odd meters apart, 50 meters apart. So it works. So we were quite happy. And then results of the fishing line, so you can see there, trial 1, as I said, was a twin rig. Skates and rays down 80%. We hit our other target of cod was down, but as even Allard was alluding to there, maybe flatfish mightn't be the best thing here, because if you lose your skates or your turbot and brill, 67% of that is down. Although in the Celtic Sea, again, these species aren't sort of in large volumes there. So you're not getting losses. We were getting losses of mostly placed and so forth. Again, and you can see trial 2, which was again in the Celtic Sea. Again, it's very consistent, 78%. Cod wasn't maybe as good, but there were differences between the 2 sort of trials in numbers of fish. I will stress that obviously, the twin trawl was simultaneous sort of assessment, and trial 2 then was alternate haul. So, but still, we sort of statistically sort of worked this out, and it has been sort of proven. So it's consistent. For the modified rigging, as we call it, this gap between the thing, again, it was it didn't work for our whiting, but you can see there 36% down on skates and rays, and even the dogfish, which were there, were almost 30% down as well. Again, catches might have been slightly low with the skates and rays, but it did work. Gaps seemed to work, and I think even following on maybe from some of Vincent's work there, maybe this is way of maybe deflecting them with some of this electrical sort of deterrence or something like this to the side or whatever, or even down would probably work. And this is the one interesting thing about this, and we're not exactly sure why creating a gap in the prawn trawl had greater catches in 30% more. But with saying that, we are going to continue on. So just a little bit of sort of where we're at with the raised fishing line. It is legislated gear, specifically in the south of Ireland, just in those ICES divisions, which is just basically the areas that hug the southern coast of Ireland and the sort of Cornish coast of the UK. We are doing, we have been doing rather more work with raised fishing line using lights. Again, it's mostly for cod and other species to avoid them. And with the lights, we're not sure what's going on there, but maybe Betty, who's coming up next, I think can talk about this maybe more specifically. I will say in one or two of the trials that we have noticed skates were down, but it was raised fishing line versus raised fishing line with lights on, lights off. There was a 10% reduction, but based on our previous work, that would have only been 20% of a potential catch. So I'm not sure it's a great, but it's always going to be small, I suppose, when we get to only 20% of the catches. But maybe, as I said, Betty can elaborate on what lights can do. Just on this raised fishing line sort of concept, we are planning sort of more work where we completely remove the ground gear and lift the trawl off the bottom. So this again should reduce or should help reduce Elasmobranch catches, or especially the rays. Modified rigging, again, it's back to what I was talking about, the quad rigs, which is the more common sort of method of catching prawns in Ireland, at least. This we will be able to simultaneously sort of assess whether the gap will work or not. Hopefully, this is planned for May this year. So we will be keeping a sort of closer eye on where the rays are with this one. And that's about it. This is just a quick sort of summary, 2 summary sheets of we spoke about this before, Irena. Just some summary sheets of the work, and I can send these on, or this will be recorded anyways, and we can work with that. So that's for me, and any questions would be good, or we can answer them at some other stage. Thank you.
We do have time for some questions. If you stop sharing, then we can see you again properly.
Yeah, I'll see how I can.
Yeah.
Where am I?
And I will, for the presentations we do have be recording, we'll probably putting them on YouTube. This is all technology that is still almost 50. It is all very exciting to me still. But I will also send, I'm very good at sending around papers. So the papers for people that I do have, I will also make a package of those and send those to the participants of the webinar. So we all have that information. And yes, these sheets, and I will probably start making those sheets for all the papers I've found so far of some people are doing.
Yeah, I think it's a good one. Yeah, and I think we have it. If you check our publications page, we have a little booklet that we'd have put out, just of just summaries, because I know nobody has the time to read 14, 15, 20-page papers. So like a little one-pager always makes sense to me.
Perfect. Thank you so much. And you already introduced her, because I don't think we are seeing any questions. If they come up, just, if people have other questions or things are just regular thing that you want to, things you're working on that you think you want our experts to have a mull over at the end of the webinar, please put them in the chat, because we like our having people bring ideas to us, because it's always there's always more in our collective hive mind of shark experts than there is in our own little brains. So the next speaker is Betty. She also asked me to not, because she is just about to defend her PhD and this has not been published. So that's why I'm also gonna pause the recording again. There we go. And if you will, you're supposed to be able to start to share your screen. So you can. Yes. Oh, and Vera, if you want to come in. Sorry, I just want to say, Vera, if you come in for any comments, we can do that after Emma's talk.
Of course, yeah, sure. Thank you for the introduction, and hello everybody. My name is Emre. I work with GFCM as a consultant. I'm based in south part of Turkey as well. And let me share my screen. Can you see it?
Yes, there we go. We can see your screen. Yes, there we go.
Okay. This study was one of the flagship of my PhD 5 years ago, almost. And we managed to publish that in the Ocean Coastal Management. And I'm here today to talk to you about how a simple technical ground gear modification can influence the bycatch of rays in the Mediterranean bottom trawl fishery. So yeah, the main objective of this study was to design a ground gear in bottom trawls that gives Elasmobranch species a chance to escape underneath the fishing line or foot drop. So the idea of the foot drop or ground gear is to maintain the seabed contact while passing over the obstacles and prevent the fishing gear from damaging. So far, several ground gear designs were developed and to optimize the catch efficiency and configuration and the materials used, depending on the seabed structure mainly and the target catch. So these are the most commonly used ground gears in the northeastern Mediterranean, where this study was conducted. So to better understand the problem, let's have a look at the study area a bit more closely. So in general, bottom trawling is one of the world's most productive yet problematic fishing methods due to its bycatch and discard ratios. And due to having mixed bottom type and large continental shelf and Mersin bays, the northeastern Mediterranean fishing ground is capable of producing bottom dwelling species like prawns and red mullets. So economically, a remarkable part of the income of fishers is provided by mainly these two species. And at the beginning of the fishing season, which is in September, and there are more than 100 bottom trawlers working in this ground and more than 130 species entering the bottom trawl quota. So according to an earlier study, the discard rates in this fishery is the 50% of the catch in terms of weight and 72% of the catch in terms of numbers. So these numbers could be a very small crab or huge marine megafauna like Elasmobranches. So as we all know, they have some special life conditions like slow growing with late attainment of sexual maturity and low fecundity. They are not commercially valuable in this area, which makes them unwanted bycatch, and they always end up being discarded. So all these information told us that we need to address the most urgent need, which is improving the selectivity for these species. And previous studies, earlier studies, show that it is hard to achieve that in the rest of the trawl body due to their morphological differences, because even the small sizes are or could be larger than the mesh sizes. So we therefore needed to focus on preventing them entering the trawl mouth in the first place. So this is one of the most commonly used ground gears in more details with some technical specifications. Fishers mostly use this one to reduce any kind of marine debris that potentially can pass through the trawl mouth. The most important thing we should focus on here, the distance between these two ropes, because it consists of two lines attached to each other with this triangle shaped rigging. and the distance in the air, it's about 5 or 6 centimeters. In fact, most of the target species, like I showed you before, the shrimps and red mullets, are small enough to be able to escape through this gap if they attempt. But some of the elasmobranches, even if they attempt, they cannot escape through this gap due to this triangle-shaped rigging. So what we did is to modify the conventional ground gear by cutting only this triangle-shaped rigging between these two rocks in the central part of the whole ground gear. The length was 2.7 meters, which corresponds to 13% of the entire ground gear. So in total, 36 fishing operations were conducted with alternate hull method, and it all included in the statistical analysis to make a catch comparison. The same troll was used to make catch comparison with and without this modification. During the tows, we also used GoPro action cameras. They were mounted in various sections and oriented directly at the center of the ground gear. Now, I'd like to show you some unwanted footages for both this traditional ground gear when it first touched the seabed, and second one, what we modified after a while. It looks exactly the same as the traditional gear, like we didn't cut it at all. So the underwater performance was checked and everything looked perfect. And we started testing these two ground gears. So what we found was very promising and interesting. Here in this table, you see 3 different unwanted bycatch species. They're all rays, guitarfish, common stingray, and butterfly ray. In this table, what we really should be focusing on is the catch ratios. For example, for the guitarfish, and this catch ratios, by the way, shows the catch efficiency of the modified ground gear. So for the guitarfish, the modified gear probability of capture for species, it's 8%, which means it's more than 90% in the traditional ground gears. For the stingray, this probability is 20% in the modified gear. On the other hand, it was 80% for the traditional gears. And our third species, the results were inconclusive because as you can see in the right bottom of the table, the white confidence intervals are quite wide. So to summarize, by modifying the ground gear, 2 out of 3 observed elasmobranches were reduced successfully, and we also checked. We also recorded the length data for the target species, and they didn't show any significant reduction in target species, but except for common sole, there was a reduction in the modified ground gear. But I'd like to specify a few points regarding the common sole. First of all, this is not a main component of the trolling. It is mainly targeted by the small-scale fishing vessels with trammel nets, and additionally, the size range of the individuals reduced in the modified ground gear was below or around the minimum landing size, which is 20 centimeters, and individuals reduced in the modified ground gear was between 17 and 22 centimeters. So to our knowledge, this was back then, this was the first study focusing on the ground gear modifications that provides the laterally increased space for unwanted bycatch of elasmobranches that are mainly found in the demersal troll catch comparison. So this video shows the fish behavior observations at the troll mouth. Our first star is a stingray. As you can see, they're always looking for an escape gap under the ground here, under the fishing line. The second one is the guitar fish. It is the same. And the butterfly ray, as you can see, whenever they touch, they contact with the ground gear, they attempt to rise and get back to the current, passing through the troll mouth. So the main reason we came up with this idea is those escape attempts that we've seen during our underwater observations. And when it comes to elasmobranches, they all do not behave in the same way. And the reason we couldn't see a reduction in butterfly weight in the catch composition was quite simple, as you can see, because in all the time we observe these species, unlike other two, they attempt to rise when they contact with the ground gear. So main conclusion of my presentation would be, I mean, prior to implementation of such modifications, studies aiming to exhibit or exploit or reveal interspecies behavioral differences should be prioritized, and we should be taking into account of potential significant loss of commercial catch in terms of fisheries economic loss, particularly in mixed species such as Northeastern Mediterranean. I think that's all from my side. Thank you for paying attention and listening. I hope you enjoyed.
Yes, if there's any questions on your work, it's again very interesting to see all these different strands coming together. Some commonalities we see, sort of like, yes, what's the objective of being selective? In your case, I mean, you're having guitar fishes in there who are strictly prohibited, so it could actually be something that would halt a fishery if you're implementing the current CMS laws on that, and say you shouldn't be having any bycatch. So in that sense, if you're looking for something that's very rare and trying to get rid of it, that's a story. Whilst when Allard was saying, you know, most of these rays have a value that the Dutch beam trawlers catch, but they catch too many of them, and it's over quota, and it's linked to this landing obligation. So that's always why science is the research is one piece in the puzzle, but you also have to have the policy, you have to have your objective, you have to have a better understanding of what is or what isn't possible. Like Allard was saying, we had this whole thing with electric fishing in the North Sea, what went a bit sour. While anything to do with electricity is now tainted here, which means can it never come back? I don't know. It's just that right now it's difficult. So this is all fascinating in a way to see how all these things fit together, because there's interactions with all the presentation we saw today. So thank you to all our speakers. If there's any questions for Emre, now would be the time to ask them. If not, his presentation is one of the ones we recorded, so that will be made available, as well as any papers that we have, including your wonderful paper, Emre, that made me find you and invite you. So, Paddy, have you any final words for the wonderful people that have stayed with us for the entire webinar?
I do, and I have great thanks to all our speakers. This has really exceeded my expectations of what we could find and listen to and hear on this subject, which is really fascinating. I mean, I've got so many ideas and thoughts about how we could go further. I won't share them now because we're running a little bit out of time, but thank you all so much. Thank you for the people joining us, for the questions. It's absolutely fascinating. Irene and I will collate this and make an advisory, but I really think there are so many strands of things we could be picking up. And I mean, 6 PhD ideas have come up already. So I really think, thank you all so much for inspiring presentations, for the questions, and for giving us so much information about how to move forward. So thank you all very much. Yes, and thank you, Irene.
Okay, thank you. Okay, so you all have my email, so if there's questions, you can email us and come up with them later. So with that, I will close this webinar. Thank you for
Thank you.
participating and see you around.